Hi everybody, welcome back. This is Unit 4, it's Unit 3, Lesson 7, and we're going to talk about the difference between fission and fusion reactions today. So fission with the S's, right? Fission with the S's is the splitting with an S. And it's the splitting of a heavy nucleus. That heavy nucleus is one of two things. It's either uranium or plutonium. So I'm just going to say like uranium. Into lighter, radioactive daughter nuclei. Okay? In order for the uranium to split, it must absorb a neutron first. So the typical reaction for fission, what you should look for is you should look for neutrons on the left of the arrow, and you should look for one or more neutrons on the right side of the arrow. Because a neutron must be absorbed by a uranium nucleus, and then that makes the uranium nucleus, as you can see here in the picture, unstable, and then it splits into daughter nuclei and 3 more neutrons. And I'm going to show you what's special about that in just a moment. So let's write a generic reaction here for fission. So the uranium-235-92 absorbs the neutron, gurgle, gurgle. It splits into daughter nuclei, which are barium and krypton. And 3 more neutrons, and releases tons of energy. So yeah, these are crazy exothermic reactions. Remember, 3 billion times more energy than an ordinary chemical reaction. And I think I have a link here of how this can happen in a controlled fashion and allow us to get power, or it can happen in an uncontrolled fashion and result in a nuclear bomb. So I want to show you the difference between those two things. Uh-oh. Okay, so here is the 2 different chain reactions in fission. Oh boy, thought there was sound. So this one on the left is a nuclear reactor, and in a controlled fission reaction, like what happens in the nuclear reactor, these rods are made out of uranium. These are called fuel rods. And within those, there's billions of uranium atoms, more than billions of uranium atoms. And these blue things are called control rods. And their job is to absorb extra neutrons so that the not too many uraniums split at once, so you don't produce too much energy all at once. So let me show you how that happens. I'll insert the control rods, and then it'll magnify this. So the control rods go in, and here we go. We'll just blow up. So these represent the uranium atoms. They're splitting, and the extra neutrons get absorbed. So not too much energy, which is represented by the waves, not too many uraniums split at once. Okay? Again, here we'll replay the controlled one. Boom. Okay? I don't know if you can tell, but as the little neutrons get to the control rods, they get absorbed. So if we go to the uncontrolled reaction, which this is representing like a little boy or fat man, one of the 2 nuclear weapons that we dropped on Japan in World War II, this is what an uncontrolled chain reaction looks like. There are no control rods. So each of the 3 neutrons makes 3 more split, which makes 3 more split, which makes 3 more split, which results in too much energy being released at once. Okay? So if it's an uncontrolled chain reaction, you get too many uranium atoms splitting because there's too many neutrons released. Okay, one more time for the uncontrolled. It's kind of scary. Good thing there's not sound. right? And this happens in like microseconds. It happens so fast. And there's so much heat and energy released that you get this expansion of all the surrounding materials. And then anything around it gets annihilated. Okay? On that note. So that's fission. It's the splitting of a heavy nucleus into lighter nuclei. It makes more neutrons, which can make more split, and radioactive waste. Not really a good thing. Oops. Where's fusion? Fusion is the combining or uniting. See, the U in fusion is for unite. So it's the uniting of light nuclei. Now, remember, nuclei are positively charged. Atoms are neutral. But if you just have the nucleus of atoms, they're both positively charged. So we're trying to bring together light nuclei. And the lightest nuclei are either hydrogen or helium. That's who you're going to bring together. Usually it's hydrogen. You've heard of a hydrogen bomb. Okay? To make something heavier. And it's not heavy by any means, but it is heavier than the original nuclei. Now, this does not require neutron absorption like fission does. But what it does require is extreme amounts of heat and pressure because you're trying to bring together two things that are positively charged. And like charges repel, right? They want to push away. So the most common example of this, you see this here. You have two different isotopes of hydrogen. Oh, except that is not hydrogen. Let me try that again because I know some of you cannot read that. And you bring them together, you unite them with lots of heat, lots of temperature, like in the sun, heat and temperature and pressure, and you make helium. And the neutron is just a byproduct. But you make lots of energy, highly exothermic, right? This actually produces more energy than fission does, okay? And the benefit of this is that the waste is not radioactive. The problem, however, is that in a fusion reaction, the temperatures that it requires to bring these nuclei together, it's just not practical. We can't do it. We've been unable to do pure fusion reactions. And the energy that's released is so much that it's hard to contain. So fusion reactions are very difficult right now. They're not used as power sources, okay? I have a little chart here just to compare the pros and cons of fission and fusion. The benefits, actually, you know what? I'd like you to fill this out. Why don't you go ahead and fill out your little chart, because I think you have that chart in your notes. Am I right, Karina? Karina's here. Do you want to see her? Karina, you want to be on camera? Oh, she doesn't. You sure? Miss Trapp might want to see you. Miss Trapp, do you want to see Karina? Look, Miss Trapp. There she is. Hey. Okay. I think I got you. Maybe I was too high. Okay, there she is. Okay. Whoops. There. Okay. So anyway, you guys fill this in, and we'll talk about it tomorrow. And then we're going to watch a little video presentation on Chernobyl. Not the Chernobyl Diaries, because I heard that's a scary movie, and I don't like scary movies, but on Chernobyl. Have a great night, everybody. We'll see you tomorrow.